The nice thing about electron configuration is typically these are skills-based problems where you just have to write down the electron configuration. There's not much explanation behind it. However, understanding the electron configuration for atoms does have applications in other things. And that's where the explanation sometimes will be brought up instead. So remember our Bohr model where you had a nucleus and then you was like rings around the sun? That also kind of represents the energy levels of the electrons. So as you go down each row of the periodic table, you're at a higher energy level. So the hydrogen row across is the first energy level, the lithium row across is the second energy level, sodium is the third, so on and so forth. So Niels Bohr, first one to kind of come up with this idea of energy levels. Hopefully that kind of rings a bell to you. Just further down you get on the periodic table, those electrons are further away from the nucleus. Two other terms to remember is a ground state and an excited state. So when we have you write the electron configurations for things, typically that's the ground state because those are where the electrons are at their lowest energy level filling up. Remember, electrons can get excited, they can jump up. So sometimes students in the past would get thrown off when the College Board questions ask for the ground state electron configuration for something. That's the same as just saying the electron configuration. The reason why they have to say ground state is that if you accidentally, instead of writing down 4s2, wrote down 5s2 for something, you could argue that, well, those electrons were excited, so they were up into the 5th energy level, and that's why I wrote it that way, and you didn't write the question to say ground state. So they're trying to avoid that issue. We will talk about light a little bit later on. So that's where, remember, ground and excited state, you might have heard of that before as well. Now, this next thing you don't have to write down. Energy levels was half the story of where electrons are located, but then we have to get into those orbitals. The S, the P, the D, the F. So it's not as simple as a Bohr diagram like planets around the sun. The Heisenberg uncertainty principle was the first thing that kind of came up with this idea that you don't know the momentum and the position of a particle at any given moment. So you just know an approximation of where it is. Schrodinger used a lot of calculus to try to show that approximation of where it is to prove that Heisenberg uncertainty principle. But because of Heisenberg and Schrodinger, we have the model that we use today for describing where electrons are located. Not only the energy level that was brought to us by Bohr, but then also the orbitals, the S, the P, the D, the F. So remember, the first two columns of the periodic table are the S orbital electrons. So your alkali metals, your alkaline earth metals. The last 6 columns are the p orbitals, so boron all over to neon on down. The d orbitals are where that dip is in the periodic table with all the transition metals. And I don't know if it was Rankin back there was asking about the f orbital before. I have not seen an AP question deal with anything from the f orbital with those two bottom rows going across. I know in Chem 1 we taught you how to read all the way down to there, like the uraniums and stuff like that. But I'm not aware of anything that bonds normally from that f orbital that we work with in Chem 1 or in AP Chem. And typically your questions are going to be multi-part questions, where part A, then, okay, what does that deal with part B, so on and so forth. We don't do nuclear chemistry in AP Chem, so then, again, we're not going to be covering a lot of that stuff. So I would say overall, don't worry too much about the f orbitals. Okay, so what I want to do, and again, energy levels. So we have two different ways to classify where electrons are located. Their energy level and their orbital. What I want to do then is I want to review writing all those different notations we learned in Chem 1. I'm going to do it for sulfur. So I'm going to switch over to the Smart Notebook to go over that example with you. shorthand notation means go to the previous noble gas. So again, noble gas configuration is the stable notation. So the previous noble gas to sulfur is going to be neon. So once you've hit neon, now you just have to finish the next row. The next row starts on the third row down, so that's 3. These are s orbitals, s, and I have to get through both of them too. So I'd write down 3s2. And after I got to magnesium, that's 3s2, I moved my way over to aluminum, which is still in the third row across, the third shell, but now we're in the p orbital. Sulfur is the 1, 2, 3, 4th element in that shell. So this would be the ground state shorthand notation for sulfur. By and large, the shorthand notation is the one you need to be most familiar with, because it shows the valence for outer electrons. That plays the role in bonding that you need to be aware of, and again, other properties of the atom. However, the long notation is going to be needed for the photoelectron spectra stuff that we have to go over here, because the photoelectron spectra is going to talk about, here's a graph to represent all these different electrons. If we were writing the full-blown electron configuration, we have to start at hydrogen, the innermost. That's the first shell, s orbital, and if it's 1s2, that covers hydrogen, which is 1s1, helium, that's 1s2. So we read the periodic table like a book, left to right, top to bottom. After you get to helium, now you go to the next line. 2s2. That gets me through beryllium. After beryllium, you have to kind of skip over that gap to get to boron. Still in the second shell, p orbital. And if I have 6 electrons, that fills all the way to neon. Because once I've done that, I've just done my shorthand notation, kind of. The ending is the same. 3s2, 3p4. Doesn't look like a 2. Okay, that looks like a weird 2 now. Okay, so this one we're going to tie into the second topic for the day on photoelectron spectrum. Orbital notation is taking what I just wrote on the top of the screen here and using those up and down arrows to show the spins of electrons, how they fill the suborbitals, things like that. So, this 1s with the up and down is the same as saying 1s2. Same goes for the 2s. Where it gets a little different is when we hit the p orbital. Because in the p orbital, there are 3 suborbitals. One of the rules that we talked about in Chem 1 was called Hund's rule, that each suborbital gets filled with 1 electron before they have to double up. So therefore, if I were filling this up, my first one there would be for boron, because that's the 5th element. There's 5 electrons shown. Carbon would be the 6th element. Then nitrogen. And now that each suborbital is filled, now they have to double up. And I show opposite spin, because that's referring to Pauli's exclusion principle. Here's oxygen, fluorine, and neon. That if you have 2 electrons in the same suborbital, you have to have opposite spin, or otherwise there'd be too much repulsion. Three s, being an up and a down. And I end in 3p4. So I draw my 3 suborbitals. I have an up, up, and an up. That's 3p3. And there's my 4th. And this gets back to, on that reading guide, if you got to the end, paramagnetic versus diamagnetic, are they all paired up? No, they're not. So this would be a paramagnetic example. Again, not vocabulary that I'm going to emphasize. I haven't seen it much, but our book goes over it, so I just wanted to briefly have that covered. So these are the 3 ways that we've represented location of electrons from Chem 1. And this is meant to be kind of a review of how we've covered that before. What the reading guide jumps into early on, and maybe I should have just started class with this and then had you do the reading guide and bring you back together, is some of those exceptions to these rules as well. So I go back to the notes here. Again, Pauli's exclusion principle is just the idea of the up and down arrows, so you don't have to actually know that term, Hund's rule. Each suborbital gets filled 1 with 1 before we add on. The build-up principle is just stating that we start with the innermost electrons and we build up from there. Okay. What you should have saw through reading guide. The transition metals, the metals in the middle of the periodic table, is where things get a little bit different. And what I mean by that is that to gain stability for a transition metal, they don't necessarily have to be an ion. I mean, your alkali metals, your first column, you don't find just sodium metal laying around neutral. It's reactive. It loses that electron to get to the octet. You don't find most alkaline earth metals, the second column, on their own. Because they're close to the octet, they can lose electrons to get there. However, you find iron on its own, you find nickel on its own, you find copper on its own. Most of those transition metals in the middle periodic table can be found neutral because there's different ways to achieve stability other than just the octet for them because they're so far away from the octet. So, half-filled orbitals are an example. I'm going to go over chromium and copper as the 2 that I'm going to talk to you about. And then my last point that you should have hopefully saw if you did on the reading guide question 2A. When transition metals are ions, they lose the outermost electrons first, which are the s electrons. And there's a lot of transition metals with a +2 charge out there. Unlike the alkaline earth metals, that doesn't get them to the octet. That just has them lose the s electrons first. So again, I want to show you chromium and copper as examples of these exceptions because really it's only those 2 columns that are any different than what we taught in Chem 1. The chromium on down column is the 4th element in the D. The copper on down column is the 9th element in the D. Those are the 2 that can take advantage of the idea of half-filled orbitals being stable. So if I do the shorthand notation for chromium, in Chem 1, we would have told you to read it like a book. Argon, 4s2, 3d4. This is what we would have told you in Chem 1. That means I have a full 4s and 4 out of 10 full in the D. I mean, think about it. That D, if I did orbital notation for it, would be like this. The 4s and the 3d are very close together. And with that, here I can even draw this one out. And with that, there's a chance that those electrons might not just be there. Because what happens is one of these actually will fill this instead. Which means this is actually going to be a 4s1, 3d5. That way, it's half full for the 4s, half full for the 3d. More stable than a full and a 4/10 full. And this follows that pattern going down that column. If I show you copper, copper is similar. Where in Chem 1 we would have said, oh, just write it as 4s2 3d9 because it's the 9th element in the d orbital. That configuration gives me a full 4s and a 9/10 full 3d. However, it's more stable to have one orbital full and one half full. 4s1 3d10. One of copper's charges, by the way, is a +1. It's one of the things that is a +1 charge in the transition metals, because it would lose that 4s1 electron right away. I believe silver was brought up in your reading guide. Silver only has one possible charge with +1. It loses its 5s1 electron right away. So WebAssign will have you type this out. You'll have a couple of examples where you have to go over either a neutral atom or an ion with its electron configuration. Again, there's a practice sheet on electron configuration that hopefully we'll have time to work on during class as well. One of the ways that we know the green version is correct versus the black is we can measure these using something called photoelectron spectroscopy. And that's what the second half of notes I want to go over with you is about, is this technique that identifies that this is the actual correct distinction of these things. And this isn't just made up of, I think this is better. This is what we've noticed. And then they try to explain what they've noticed. So, photoelectron spectroscopy is often called PES, photoelectron spectroscopy. Gets back to the idea of ground state versus excited electrons. Remember in Chem 1, energy is added to an atom. That could be heat energy. If you put it in the fire, it could be electrical energy when you flip on a light switch, and that's why these lights are on. Energy is added to an electron. They jump up, they fall back down. As they fall back down, they give off that energy in the form of light. Depending upon how much energy they absorb, it could be visible light, your Roy G. Biv. It could be invisible light, like infrared if it's low energy, microwaves if it's low energy. High energy can be X-rays, gamma rays, things like that. But what if we zap an atom with so much energy that that electron jumps up and it doesn't come back down? After all, what causes it to come back down is attraction to the nucleus. So if you really pound it with energy, and usually this has to take X-ray level energy or higher, you can cause that electron to jump up, but now it's no longer attracted to the nucleus and it's just gone. You're emitting an electron, you're getting rid of it. That's what my steps are trying to say, is that the atom absorbs a certain amount of energy, that makes it jump, but then it's gone. This, by the way, is one of the techniques that we can use to measure ionization energy, a trend in the periodic table that we're talking about next class. So again, we're tying in electrons, photoelectron spectroscopy, and then trends all this week. And this is an application of Coulomb's law, which is brought up on your goal sheet today. Coulomb's law is just talking about the fact that the attraction between two particles is due to their distance between them and the charge between them. Now, there's an equation that was given for Coulomb's law on your goal sheet. I've never seen that equation used ever. It's more there for a reminder of this principle. So in other words, if electrons are closer to the nucleus, they should require more energy to be ejected. Because if they're closer, there's more attraction. That's what Coulomb's laws kind of state. I like to use the analogy of long-distance relationships, that if any of you have a significant other, when you go off to college, you're no longer in the same city, it's hard for you to have the same level of attraction towards someone if you never see that individual. However, in high school still, there is very close proximity and perhaps a little too much attraction between individuals in a couple. Right, Nelson? Either of you have seen this? Couples just a little too close in high school. You don't get that in college. So my last slide will hopefully tie in how this is related to electron configuration. And the good news for you is when you work on that packet coming up here, you'll be practicing electron configuration after a while. So it does all tie in together. So on the smartboard is a graph. This is a typical PES, photoelectron spectroscopy graph. And what it shows on the x-axis is the amount of energy it takes to eject electrons. The y-axis is the relative number of electrons. So they kind of show peaks. This peak is worth 2 electrons. This is worth 2. This is worth 6. This is worth 2. This is worth 1. Our goal today, and unfortunately WebAssign does not have PES graphs on it at all, so your WebAssign is going to be more on electron configuration. But that's where the AP Classroom stuff does have this. Our goal today is to look at something like this and be able to identify what element it is based on its electron configuration. And what I mean by that is, let's look at the x-axis. On the bottom graph, it starts at 0.0 and goes up past 10. Because there's different energy levels for different electrons being lost, there's a second graph where it starts at 100, 500, so on and so forth. What I can tell you by looking at this graph is that this peak right here with 2 electrons is the highest energy. 151 megajoules per mole is needed to eject those 2 electrons. If that's the highest energy, that must be the innermost electrons. That peak represents 1s2. Are we okay with that statement? I know it's kind of weird that the graph has sections to it, but if they tried to keep the same increments to go up there, it'd be too difficult. Again, these are the innermost electrons, which means they have the most attraction to a positive nucleus. They're the hardest to remove. After that, here's this next peak at 12.1. 2 electrons are lost. This must be the 2s2 peak. Next is 6 electrons. Well, this peak represents 2p6, the next on the periodic table. Then we get to here, these 2 electrons must be 3s2. It makes this 1 electron here, 3p1. And if I look on the periodic table, what element ends in 3p1? It's aluminum. So this would be the photoelectron spectroscopy graph for aluminum. Again, the 3p1 is the outermost electrons. Therefore, it requires the least amount of energy to lose them. They are further away from the nucleus. And there's only 1 there, so it's easier to lose. How we know that when you get into the transition metals, it's a 4s1 3d5 for chromium is they've done the measurements. They've seen that there's a peak for 5 electrons in the 3d, and then the outer 4s1 is the easiest one to lose. Again, this supports also, if you are going to lose electrons, you lose the outermost because they require the least amount of energy to lose. So my hope is, for those of you who are still a little rusty on electron configuration, as you do that POGO packet on photoelectron spectroscopy that tries to explain this concept, and it tries to simplify it by, dealing with soccer. Because if you can explain things in terms of soccer, that's a pretty simple sport. I mean, 3-year-olds play soccer. Do we have any soccer players in here? Yeah, that's right.
making fun of your sport. But then as you get through the packet, it's going to start showing you graphs and getting you practicing with this. So if we can figure out this, and then we can also deal with the transition metals, that's really our goals for today.